Welcome to the Foundry by Forge College. Grab your clipboards and hard hats, because today we are diving into validating full transactions end-to-end. In our last explainer, we unpacked the super fascinating world of signature creation and verification, learning exactly how cryptography binds a specific person to a specific action. But today, we're stepping into a completely new role. We are the blueprint inspectors. We've got this newly assembled transaction machine sitting right in front of us, built with structure, scripts, and those cryptographic signatures we just learned about. Now, our job is to rigorously test the whole thing end to end and make sure it actually runs before it gets anywhere near the live Bitcoin network. So the big question is, do the keys actually open the locks inside the assembled machine? Look, having authorization signatures is great, right? It's kind of like having a VIP backstage pass. But now we gotta test if those signatures actually satisfy the strict mechanical requirements of a full transaction. Seriously, it doesn't matter if you have a perfectly forged, mathematically sound key if you're trying to stick it into a lock that expects a completely different shape, or, if the door frame itself is totally broken. We absolutely have to verify that all the pieces interact flawlessly. To test this out without getting overwhelmed, we're gonna follow a highly logical three-step inspector's checklist. First up is Pillar 1, structural parsing. Then we move to Pillar 2, script execution. And finally, Pillar 3, signature verification. All right, let's jump right into Pillar 1, structural parsing. You got to remember that Bitcoin nodes are ruthless inspectors. When parsing, we check the numeric version, we strictly count the inputs and outputs, and we look for specific witness flags. And the most important part? Absolutely zero trailing data. If there is even one single leftover byte tacked onto the end of the raw hex, boom, the blueprint goes straight in the trash. It's literally like finding a random leftover screw after building a jet engine. It's an instant failure. The bytes you feed into the hashing engine must be absolutely perfect, or the whole machine just breaks down. Moving right along, let's look at Pillar 2, script execution. So how does this engine actually work? Well, we start with a clean slate, basically an empty execution stack. Think of the stack like a bare workbench. What's the very first thing we do? We drop our unlocking data right onto it. For a legacy pay-to-public key hash script, this means our signature and public key land squarely on the workbench. Next, we execute the locking script opcodes, the script pub key, which act like a series of mechanical tests against that unlocking data. We duplicate the key, we hash it, and we check if it matches the expected lock. We're essentially watching the gears mesh together step by step. Eventually, those gears hit a specific instruction called op_checksig. Now, don't let the technical name intimidate you. op_checksig is really just a standard engineering protocol. It simply pops the signature and the public key off our workbench and mathematically verifies them against the transaction digest. It's the ultimate moment of truth, where the machine asks, is this unlocking data genuinely authorized to spend the specific output? It really demystifies the whole process by treating the cryptography as just another mechanical gear in the sequence. And here is the absolutely crucial point. The stack must yield a single true value. After all the dust settles on our workbench, the engine makes a binary demand. It must see one and only one true left behind. There are no points for participation here, and definitely no points for just being close. If it evaluates to false, or if there's any leftover garbage sitting on the stack, the transaction fails the mechanism test right then and there. No exceptions. Which brings us finally to Pillar 3, signature verification. To really verify signatures, we have to understand the sighash preimage. This is the exact subset of transaction bytes that are deterministically chosen, serialized, and hashed. The signer is committing to this specific digest. So when someone uses a flag like sighash all, they're basically stamping their signature across almost the entire blueprint. That locks it down and prevents anyone else from making unauthorized modifications to the inputs or outputs. It completely dictates the exact rules of the commitment. Now, here is a super practical inspector's tip that'll honestly save you hours of headaches down the line. Always log the exact sighash preimage hex before you attempt to verify the signature. Why? Because formatting errors and slight differences at the preimage serialization stage are by far the #1 cause of signature mismatches. If the bytes you're checking are even slightly out of order compared to what the signer originally signed, the mathematical verification is going to fail every single time. Okay, so we've got the theory down, but how does this actually look in the real world? When students run through these exercises in our hands-on learning programs, they quickly realize that no modern inspector is out there verifying double-shot 256 hashes completely by hand with a pencil and an abacus.
I mean, it's just not practical to manually serialize hundreds of bytes and calculate all that complex cryptography yourself.
Instead, we use a hybrid approach, pairing manual reasoning with an AI-assisted validator. Look, doing all the math manually is slow and incredibly error-prone. But if we fire up an AI-assisted local Python tool, we get the absolute best of both worlds. The tool speeds up the repetitive, tedious execution like the hashing and stack simulations, but the human inspector still meticulously audits the logs. The tool doesn't replace our manual reasoning, it just gives us a much faster magnifying glass to read the blueprint. If you decide to build a local Python validator, here are the exact tasks it should handle for you. It should take the raw hex, the UTXO-JSON, and the input index. Then it should automatically build the sighash hash all preimage, compute that double SHA-256 digest, and brilliantly print out a step-by-step stack trace for you to review. But hey, a really quick and highly necessary safety warning: keep this tool offline. Do not use network calls or broadcast anything. You are just testing locally in a totally safe environment. And that brings us to the ultimate validation log table. Think of this as your master checklist. This concrete artifact documents the pass or fail state of your entire mechanical inspection. You confirm the parsing to prevent malformations. You confirm script stack transitions to validate the unlocking logic. And you confirm the signature math to guarantee cryptographically secure spend authority. If all rows in this table check out with flying colors, well, your blueprint is structurally and mechanically sound. Once those three foundational pillars pass, there is just one final, relatively simple check. You just gotta confirm the math actually works out. Check if your total input values properly cover your total output values plus the required minor fees. You'll also want to check that sequence and locktime constraints are valid. It's basically the final accounting check after your deep mechanical inspection is totally complete. Ultimately, what you really need to take away from this explainer today is this: structural integrity sets the stage for transferring actual value. This rigorous, completely uncompromising mechanical validation is the unbending foundation of the entire Bitcoin system. Before a single Satoshi of fee or value can be securely transferred across the network, every single structural, scripted, and cryptographic gear must turn flawlessly in unison. It's exactly what makes the whole system so incredibly trustworthy. And that wraps up our end-to-end inspection. Exploring how these intricate pieces assemble and validate is exactly the kind of foundational knowledge we love to share. To dive deeper into this subject, run your own transaction experiments, and explore other fascinating Web3 topics, be sure to check out forge.college. But before you head out, ask yourself, if the network rejects even a single misplaced byte, how bulletproof is your own transaction code? Keep exploring, keep validating, and I'll catch you in the next explainer.